Hello everyone, my name is Lulai. Today I'm going to introduce a novel tool offered by the RADON framework called the Decomposition tool. First, I will give a brief introduction to the RADON Decomposition tool. Then, the TOSCA extension needed by the tool is described. The RADON Decomposition tool provides four features: architecture decomposition, deployment optimization, accuracy enhancement, and assignment consolidation. We will look into these four features one by one. RADON decomposition tool is present to help users find the optimal decomposition solution for application based on the microservices architectural style and the serverless FaaS paradigm. The tool can help with the plan, deploy, continuous feedback stages in a DevOps lifecycle. Why we need the RADON decomposition tool? Because refactoring the architecture of a monolithic application is never an easy job for developers. There are different granularity levels for a decomposition solution: coarse-grained, fine-grained, and mixed-grained. Cloud applications today use different or heterogeneous technologies, including virtual machines, containers, serverless functions, object storage, data pipelines, etc. Other things are needed to be taken into account when decomposing the architecture of a monolithic application. For example, security and privacy. Given a decomposition solution, we also need to find the optimal deployment scheme that can minimize the operating costs on the target platform and satisfy the specified performance requirements. For example, for FaaS-based application, we need to decide the memory and the concurrency of a serverless function. As mentioned earlier, the RADON decomposition tool can be used in four typical scenarios: architecture decomposition, deployment optimization, accuracy enhancement, and assignment consolidation. Please refer to this repository for more details. Next, I will describe the TOSCA extension needed by the RADON decomposition tool. The RADON decomposition tool is developed based on layered queue network, which is a performance modeling formalism that is particularly useful for describing distributed systems. A layered queue network can be considered as a directed graph of software and hardware entities and their dependencies. Layered queue networks provide some basic concepts. Tasks represent software entities, while processors represent hardware entities. A task contains a set of entries that represent the different operations provided by the software entity. The entry contains a set of activities that represent execution steps of the operation. Each task is hosted on a single processor. The activity may send synchronous or asynchronous requests to the entries of other tasks. A simple layered queue network is shown on the right-hand side. In order to incorporate layered queue networks into TOSCA, we introduce an abstract layer of node and relationship types. Each abstract node type contains a special property called entries. and each abstract relationship type contains a special entry, properties called interactions. We have also developed a specific set of data types to support these two special properties. Two performance policy types, mean response time and mean total response time, are also introduced in order to specify performance requirements in TOSCA. One feature of the RADON decomposition tool is architecture decomposition. To use this feature, a software designer needs to build an abstract TOSCA model and define the interface specification. Then they can start architecture decomposition by right-clicking the search template and selecting the Decompose button. The Decomposition tool plugin inside the RADON IDE will upload the service template to the public service and execute the decomposition program. After the decomposition procedure completes, the service template will be backed up and updated for the user to view the decomposition solution. We identify two types of decompositions, that is, coarse-grained and fine-grained. Coarse-grained decomposition aims to decompose a monolithic application into microservices. We use the web application node type to represent a monolithic application. A web application contains two special properties called granularity and entries. The granularity property specifies the decomposition granularity, while the entries property specifies operations provided by the API. In this example, there are 6 entries: upload image, resize image, download image, upload video, convert video, and download video. For coarse-grained decomposition, the decomposition tool will decompose a web application into container applications, which represent the microservices. This is done by clustering entries into different groups according to their semantic similarities. Now I will show how to use the architecture decomposition feature in this example. We have already imported the model into the RADON IDE and named it Model App. To start architecture decomposition of the model, we can right-click Service Template and select the Decompose button. Information about the decomposition procedure will be displayed in the output window. After the procedure completes, we can see that the web application is decomposed into 2 container applications. One implements image operations, and the other implements video operations. Fine-grained decomposition aims to decompose a microservice application into serverless functions. We use the container application node type to represent a microservice application. Similar to a web application, a container application contains two special properties, namely granularity and entries. Again, the granularity property specifies the decomposition granularity, while the entries property specifies operations provided by the API. In this example, there are three entries: upload image, recite image, and download image. For fine-grained decomposition, the decomposition tool will decompose a container application into functions, each of which has a single entry. An object storage node will also be added for the functions to share common data. Next, I will show how to use the architecture decomposition feature in this example. We have imported the model into the RADON IDE and named it microapp. To decompose the architecture of the model, again, we right-click the service template and select the Decompose button. Information about the decomposition procedure can be found in the output window. After the procedure completes, the container application is decomposed into three functions. Each implements a single operation. These functions also have access to an additional object storage node. The RADON decomposition tool can be used for deployment optimization as well. To this end, an operations engineer needs to build a concrete TOSCA model, define the performance specification, and benchmark the current deployment. Then, they can start deployment optimization by right-clicking the service template and selecting the Optimize button. The decomposition tool plugin inside the RADON IDE will upload the service template to the public service and execute the optimization program. After the optimization procedure completes, the service template will be backed up and updated for the user to view the optimization solution. Let's take a typical FaaS-based application, thumbnail generation, as an example. This application consists of two S3 buckets named upload and thumbnails, and one Lambda function named create thumbnail. When an image is put into the upload bucket, S3 produces an event to invoke the create thumbnail function. The create thumbnail function then gets the image from the upload bucket, resize it, and put the result into the thumbnails bucket. Suppose the reference workload of the application is an open workload with an mean interarrival time of 2 seconds. Also, the mean response time of an invocation to the create thumbnail function is required to be no more than 1.5 seconds. We want to find the optimal memory and concurrency of the create thumbnail function such that the total operating cost is minimized under the performance requirement. This is the RADON model of the thumbnail generation application. We use the open workload node type to represent the reference workload of the application. The performance requirement is specified through a mean response time policy. The memory and the concurrency of the create thumbnail function are defined as properties. Now I will show how to use the deployment optimization feature in this example. We have already imported the model into the RADON IDE and named it Demo App. Notice that the current memory and the concurrency of the create thumbnail function are 128 megabytes and 1 respectively. To start deployment optimization of the model, we can right-click the service template and select the Optimize button. Information about the optimization procedure will be displayed in the output window. After the optimization procedure complete, we can see that the memory and the concurrency of the create thumbnail function are changed to 256 megabytes and 4 respectively, which lead to the minimum total operating cost under the performance requirement. Additional information about the result will also be reported, including predictions of the total operating cost and the performance measures under consideration.
Hello, my name is Jose, and I will take over from here to present the accuracy enhancement feature. First, let's talk about our motivation, which in this case are resource demands. Resource demands are a key parameter of performance models that in most systems cannot be measured directly. That is why we now turn our attention on how to estimate demand values automatically by using RADON's flexibility to support external monitoring tools and libraries. To obtain these estimates, we will be using the enhancement feature, which is integrated into the decomposition tool, and that requires as an input some monitoring data such as distributed traces. Distributed tracing allows us to track a single request traversing across multiple functions. By doing so, we can collect data on each request that will help us present, analyze, and visualize the request in detail. This will help us also to understand the flow and pinpoint performance issues occurring in the system. Here, we would like to introduce Amazon X-Ray as our monitoring tool for serverless functions. Amazon X-Ray is a distributed tracing system that is natively supported by Amazon Lambda and can work with different development languages such as Java and Python. To ensure its complete automation, users can easily integrate and enable Amazon X-Ray during deployment with X-Opera. The following is an example on how users can work with Amazon X-Ray to retrieve distributed traces of Lambda functions. This is a process that interacts directly with Amazon S3 bucket. First, users need to instrument language-specific codes with X-Ray SDK to enable the global recorder in the Lambda handler. In this bit, users can further customize their own subsegments to record the performance of a particular section of the code. Then, Amazon X-Ray is activated during deployment with Lambda API. After the monitoring is finished, users can use Amazon CLI to get the trace information in a text file. The traces collected by Amazon X-Ray contain valuable information regarding the underlying Lambda functions. Information such as the execution time, That includes the time spent in the queue, memory configuration of the Lambda functions, and also the start and end timestamps, among other variables that can be used to provide regression-based estimates. As we have mentioned, the enhancement feature is integrated into RADON's decomposition tool. And for it to be called, the user needs to provide the retrieved traces in a log file along the original TOSCA model template for its posterior update. Once the traces have been uploaded, the enhancement feature parses this information and provides the demands using a linear regression model. As an example, we present an NLP pipeline, which is comprised of two Amazon Lambda functions, which are named NERL1 and POSL1. To use the enhancement feature, we have already retrieved traces from Amazon X-Ray by considering one user and a thinking time of 10 seconds. With the information provided in these traces, the accuracy enhancement feature provides a demand estimate based on a mean value regression approach, which basically establishes that the mean response time will be equal to the demand times the mean queue length observed at arrival. Now we can go to the demo. The first thing we can show is how to get traces from the Amazon X-Ray. In order to achieve this, the first thing we can do is to list the trace IDs by using the getTraceSummaries API. This will be done by specifying the start and an end timestamp. Here, we can particularly specify the key value ID in the query and show the list of IDs. Then, this list of IDs can be used to get multiple traces from the API. In this example, we use the trace IDs as our querying, and we can finally have access to the traces that can be saved as a text file. In order to use the enhancement feature, these are the two files that the user needs to upload to the system. On one side, we have the TOSCA model that contains all the specifications of the pipeline. In particular, we're going to be interested in the characteristics of the NERL1 function and the POSL1 function, just as we described in the slides. We can also have a look at the traces generated by the Amazon X-Ray service. We can also see lots of information regarding the name, the region, the timestamps, among other variables. Once the user has all this information, we can create a binary repository in the Eclipse instance. In this section, we only have to add the name, which in this case will be the NLP pipeline, which is a suitable name for the example we're presenting. Once we add and it successfully saved the component, we can open it using the IDE. This will take some seconds. And when it opens, we're going to be able to change the TOSCA template for the one we have previously defined. Once the template is uploaded, the next step is to upload the traces. With all this information, we can finally activate the enhancement feature, which also will take us several seconds to finish running. Once it's finished, we're going to be able to observe a backup service template TOSCA model, and of course, the updated one. In the backup, we can go back and look at the activity in the NERL1 function, which is 4.711. And in the updated model, we can go and check to see that it has finally changed.
Hello everyone, I am Lefteris and I will continue from here. This talk is about the assignment consolidation. In this project, we are trying to assign microservices to hosts in such a way that we avoid interference as much as possible among the microservices. We use an assignment module which takes as input the monitoring data and the number of microservices. In this case, we see here 3 microservices, and assigns them to servers from 1 to n in the private cloud environment. The user can also use the CTT to run tests on the microservices. The interference-aware assignment procedure is as follows. We begin by running some tests on the microservices using the CTT. Both the data and the TOSCA model need to be available on CHE. The optimization feature is formulated by a variant of the bin packing problem, and the genetic algorithm is used as a solution method. The optimization feature makes successive calls to a neural network in every iteration of the algorithm to get the values of the interference. Finally, the TOSCA model is updated with the assignments and it is output. Now, about the motivation. It is time-consuming for complex workloads to test every job behavior under different resource configurations to assign it to a particular class. Furthermore, collocated jobs may affect each other during the runtime, which makes it hard to cover all the possible combinations of workload behaviors. As an example, consider the following case of 10 types of jobs. If we consider all the 2 possible jobs combinations running at the same time, the running time then will be 10 to the power of 2, which is doable. However, if we consider all 4 possible jobs combinations running at the same time, the running time raises to the 10 to the power of 4, which is very time-consuming. That is why we need to train a neural network to generalize it to cover more than 2 jobs at the same time. In this part of the RADON project, we developed an interference estimation based on neural networks to estimate interference between collocated microservices within the same computing environment. An AI-driven model is implemented to predict the interference, which may cause low system utilization or saturated system resources. The training data that were used are the following. Data that is collected from SHAR command, CPU run queue size, that is the number of active threads in the system, hyperthreading, CPU nice, which means that each job has different priority, and the list of microservices that will be allocated to the servers. The neural network output is the prediction of throughput for a given task assignment to the host. Now, some information about the model. The model is agnostic of the business logic internal to each job. It is learned from the data applying artificial neural networks, and it is compared with queuing theoretic model on historical measurements. The model captures multi-threading, operating system scheduling, and job priorities. A validation on 2,500 experiments based on the DACAPO benchmarking suite has been carried out, confirming the predictive capabilities of the model. Now, about the methods and techniques that were used, the data were devised as follows. 70% was used for training, 15% was used for validation, and the remaining 15% was used for testing. The regression neural network used a hidden layer size and was trained using a function for gradient backpropagation. Then the model was validated, and it later was tested using the testing dataset. When running 2 benchmarks together, the CPU utilization is typically around 70 to 90% on machines with 8 to 16 logical cores. With 4 benchmarks, the machines were always saturated near 100% utilization. We also varied the the benchmark mix to the hyper-threading setup, the job priorities, and randomize the sleep time in between successive runs of the benchmarks. Now, when the training was done on 2 jobs to predict 4 jobs, and the testing was done in the proposed model for 4 jobs against 3 other methods, which were the queuing theory, the operation analysis, and the no model. As can be seen on the figure on the right, the model is pretty accurate when we try to predict 4 jobs, and when compared to the operational analysis, no model, and queuing theory models, using the mean percentage error as can be seen in the figure here. Thank you. This is the environment of the RADON IDE. As we can see here is an example of a TOSCA model. After this upload, the neural network is trained on the fly. As an example, we can see here that the Docker application 0, is connected by a relationship with Docker engine 0. This is a tentative allocation at the beginning. We will now proceed to look at the graphical representation of the model. Here we can see the relationship between a Docker engine and the Docker application. We will now run the consolidation. Now, this is the updated TOSCA model. We can now see that the Docker application 0 is connected by a relationship to Docker engine 1 now. Now we will see the graphical representation after refreshing the page here. So this is the new graphical representation, and we can see the new relationships between the Docker engines and the Docker applications. Thank you.